Yeah, go for it.
Sweet. Cool. So yeah, we'll be reading from the paper today, but I'll kind of go over all the important things. Yeah, at the end of the day, so we're kind of this is a really interesting paper about kind of like agent planning and decomposition, which obviously is like very high in the forefront of people's interest if you're working with agents. Um, yeah, not sure how much all of you have done this, but there's a lot of kind of basic frameworks. Like React is the most popular, I would say. I think both Llama Index, LangChain, all of them kind of have been adopting that and making it increasing its popularity a lot. And essentially, these frameworks, they even like Sui Agent and like those types of things also do some like kind of basic React like flow. And what it's doing, it's essentially greedy planning, like for every step, what's the next best action it can take. It takes that action, and then kind of at the next step, it's like, oh, okay, now what can I take next? And it just does like this one-step planning, and that is kind of what leads to a lot of the poor behavior that you might see in agents today, in the sense that they kind of go in infinite loops, they go off track, um, they, all of this kind of behavior largely stems from this kind of inability to like do long-term planning and figure out um, how to kind of like self-correct and orient. So that's kind of what this paper is addressing. It is trying to find a way to combine long-term planning um, with kind of the step-by-step reasoning logic, right? So yeah, as you can see here, what it does is yeah, so that's the main premise of this paper, right? It's trying to mitigate the challenges with React. Yeah, so it kind of has a good summary here. Prior works on using LLMs for decision making, such as React, iteratively generate the next action to be executed in the environment, given the history of actions and observations. However, as the tasks become more complex, LLMs struggle due to their limited composition ability and inability to deal with the distractors in a long action observation trajectory. So what they're trying to do is essentially compose both of these, right? Um, to address these shortcomings of kind of doing greedy planning, they introduce as needed decomposition and planning for complex tasks, or ADaPT, an approach that explicitly plans and decomposes complex subtasks as needed when the LLM is unable to execute them. ADaPT recursively decomposes subtasks to adapt to both task complexity and LLM capability. um, yeah, so essentially what if you can think about it as, it first comes up with a generic plan. It tries to execute that. If any of those subtasks fail, it recursively will pass that subtask in and decompose that into another list of steps, and then kind of keep trying to go through those more granular planning steps. And if any of those fail, it kind of like does that recursively. And I mean, you can set like a max depth iteration, etc. But the goal here is, as it gets information from previous steps, right? So it's able to plan, like decompose the subtasks better the next time around, right? So if initially it's like super vague, go to the cabinet, clean the mug, and then put the mug for drying, right? But then when it goes to the cabinet, if it doesn't find the mug, then it needs to now decompose that into like search for the mug here, search for the mug there, search for the mug in this other place. And then once it's found the mug, now it can go back and try to address the cleaning task. And then there might be like 5 or 6 steps with cleaning as well. So that's kind of how high level they're thinking about it. Um, and yeah, they kind of build this by building two different types of components, right? So they say to address such failures, they propose an as needed decomposition and planning for complex tasks, a recursive algorithm that further decomposes subtasks when necessary to dynamically accommodate task complexity. We utilize separate planner and executor LLM modules within our framework, but only decompose a task using the planner if the executor LLM detects a failure. So yeah, this is kind of what I was mentioning is if any of the subtasks fail, um, it reverts so that, yeah, the executor will first go through and try to do it. If anything fails, they shoot it back to the planner to decompose it again, add all those new kind of subtasks on the queue, and then kind of work through those again, and do that recursively.
Fails. It failed or it is failing the task.
Yeah, so I mean, I think this diagram is probably useful, right? So it kind of compares the three different approaches. So there's, yeah, other than React, there's also like a plan and execute, right? And plan execute just says, hey, these are. I mean, this is, it's really funny because this is like the most obvious thing you would think about when you're looking at this, but this came out in April, so clearly it's not mainstream yet. But it seems so obvious. Anyway, so yeah, if you look at plan and execute, it comes up with these three steps beforehand. If any of them fail, it's kind of unable to progress because its original plan died. Um, an iterative executor or React, it just does that every step of the process. So it's like, okay, if my goal is to put the mug, it'll come up with step one, then I'll try to evaluate that, and then come up with another step. Um, but it's like not able to course correct very well because it's like greedily planning. But in ADaPT, it does kind of the recursive decomposition, right? So um, in this situation, it tries to first come up with this execution, right? um, and it comes up with this plan. And they also have an interesting way of decomposing. It's almost like prompt augmentation in the sense that they take the request, and they kind of concatenate it with like ands or ors, right? So an or clause gives it like flexibility. So like I don't know if, yeah, they have this example here, right? So if they're trying to find the mug, um, they give it a few options: find and take the mug from countertops, or find and take the mug for cabinets. So it's essentially just adding robustness to it by kind of creating this like or situation where it can explore a few different paths before it comes to the conclusion that it is unsuccessful. And then the and is just kind of like, obviously sequentially you do one, two, and then three, and then four, and so forth. um so it executes task, it comes up with a plan, and it takes this plan and then it kind of goes into it and tries to do the first one, find and take the mug. It again, it's not able to just find and take the mug, so then they plan again, and this one plans like in more detail with this kind of augmentation approach. And then, okay, so step 1A failed, it's not on the countertop. So then it goes to step 1B and it finds it on the cabinet, right? And then it goes back to its overall plan here. It tries to clean the mug and then put it on the desk. Um, so yeah, I mean, it seems like the most intuitive thing you would come up with, but they've actually kind of just built this basic recursive algorithm that dynamically decomposes the subtasks. Um, yeah, and these are obviously kind of the main few things it does. Um, it's a recursive algorithm that dynamically decomposes complex subtasks on, what is that? On an as needed basis, intervening only if the task is too complex for the executor. And then they kind of evaluate this on these different simulator environments, with various tasks, right? Elf World, Web Shop, TextCraft. Um, Yeah, and then they use 3.5, comparing against React and the plan and act. And yeah, they just kind of prove out that this kind of recursive decomposition is useful. Um, so yeah, I think the general background, I think we've gone over a lot of these papers, but there's a few that try to do like learning from trajectories. There's the other set of the papers that try to do like few-shot prompting to build agents that reason about the current state and generate next actions. Um, but yeah, obviously the main thing this paper is trying to address is the iterative approach to kind of not knowing what the next best step is at every step in time. Um, And then they say, yeah, several follow-up works improve on the React by incorporating feedback in future trials, or using LLMs to develop heuristics for search. In contrast to ADaPT, they do not employ task decomposition, leading to unnecessary computation as they explore multiple trajectories or trials for the whole task. even though the LLM struggles with just one subtask. So yeah, I think this one it's kind of it's not generating multiple long range trajectories and trying to predict failure points and mitigate them in advance. It just every failure it just uses that as a point, you know, point in time in order to decompose that task further and put all those new tasks into the execution queue for the LLM. And then there's this other set of work on essentially task decomposition. So you can see that there's the few shot black box LLMs, the paradigm of programmatic decomposition into LLMs. A lot of, yeah, again, these are kind of more tasks along overall planning, but then it doesn't really have this kind of recursive decomposition, which is what they're trying to work in, is like adapting it based off of the previous stages and using that in order to generate the next step. And then, yeah, the last thing is this kind of hierarchy business. Again, it's just a system of having like multiple layers of reasoning before it generates the like final output. Cool. So that's kind of, I mean, I think we've gone over some of the previous work, but there's obviously more, and I think it all kind of falls under these different groups of either greedy planning or kind of longer range planning. And the ones that are more in this decomposition world, I mean, obviously I have not read through all of these like 10 or 20 papers that they've listed, but what ADaPT is claiming to do is that they're trying to just do decomposition when and where needed when subtasks fail, and then kind of having that um, kind of dynamic hierarchy of tasks that you need to complete. Um, cool. Any questions so far?
No.
Cool. Um, yeah, as mentioned now, I think the rest of the paper just kind of dives deeper into how these executors and planners work. But yeah, kind of no surprises, as I said. So yeah, the methodology is essentially just having an executor and a planner. The executor is responsible for. So I think one of the big things that they do is like now, in order to do this right, because if you think about kind of applying this in your project or in like a real some sort of a product, right? I think the biggest challenge here is it becomes this decomposition kind of being able to support a super wide variety of different tasks, right? Because right now, there's two options, right? There's the world of agents that came out very early on with like function calling, right? There's a lot of OpenAI agent, like all of these things that are literally wrappers around LLM function calling ability. And what it does is it's like, okay, you take the question, it has like a list of 30 functions. You try to figure out which of those functions work best. You call it, hope for the best, and then that's it. And then it moves on, right? Um, so the challenge here, right, is it's not actually directly mapping to a predefined function. It's just kind of on the fly coming up with a description, right? It can be anything. And then from there, it's kind of assuming that it knows how to take those actions, or there's some sort of capabilities defined for it to do so. Um, so what happens there is um, they kind of really are working on this idea of like very low level atomic skills, which is kind of one of the challenges of putting this into production, right? It's like you if you say go search for it on the countertop, go search for it on the cabinet, go search for it in the stove or something. It needs to be able to decompose that and like ideally do some sort of a function call or exploration or know how to triage. Um, like you need to have the idea of a atomic unit that once it's decomposed to that atomic unit, it needs to be nearly failure proof essentially. Um, So yeah, that's what they kind of make this assertion here, right? Like consistent with this one paper, we provide the LLM with in-context demonstrations of low-level atomic skills specific to the environment, such as knowing how to correctly heat objects in ELF world. This approach offers two advantages. It allows us to employ the same executor with environment-specific knowledge for all baselines and enables the planner to work at a higher level of abstraction, leveraging the LLM's general world knowledge. Um, so I think in reality, the way you would, at least the way I'm thinking of trying to use this framework is you would want to essentially fine tune these models such that they have a good understanding of what these atomic skills are. Um, so that's kind of, yeah, they do this with in context demonstrations, like, so just kind of in the prompt, but you can also tune these models, I'd imagine, so that it knows very well what those atomic skill sets are. And when it's trying to decompose, it tries to decompose it such that it'll end up resulting in these atomic skills. So that's that's kind of one thing to keep in mind because unlike like function calling agents, it's not essentially choosing amongst a function that's already defined. It's like coming up with its own plan and then kind of assuming that over time, as it keeps decomposing it, it will end up in these atomic functions that it already knows how to do and you've kind of taught it. So yeah, that's just one thing to keep in mind. Like if you're trying to actually um,
So
implement.
it's like it will recursively keep going to a level where the endpoint is the functions that we have already defined, right?
Yeah, I mean, so in this situation, yeah, kind of. So here it's a little different. Like they don't actually do this necessarily with function calling. It's within, so they have these environments, right? And the environments have kind of very specific things. It's just like, as I said, right, like it's a simulation environment too. So it's not necessarily interacting with any real world anything. It's
Mm-hmm.
like they have some sort of idea of like, okay, you can check your inventory or you can like move, and you can like take this action. But what I'm trying to say is like in practice, right, if you're trying to build this for like a real application, you'll probably use function calling. You probably need to define these functions. You need to have some sort of idea of like what these atomic functions and uses are.
Yeah.
Yeah. So I mean, this is just kind of how the executors and planners work, right? um, Use of the LLM as an executor to interact iteratively with the environment, along with example execution trajectory, overall recursive algorithm, depth k is less than d max. So yeah, it doesn't keep going on forever. That embeds the executor and planner. Yeah, I refer to algorithm one, and then outline of using the LLM as a planner to generate subtasks and logical operators before combining them. So algorithm one, we can like look at that quickly. Where is it? There we go. Yeah. So I mean, obviously, as you said, it's like very simple. It's this is just kind of writing it in pseudocode, but um, adapt generates success heuristic value completed for task T. Initialize with k equals 1. Base case terminate on reaching maximum depth. If k is greater than d max, return false. Execute the task subtasks to assess if the LLM can directly perform it using LLM generated success. Um, yeah, and then this executor LLM will tell you if it's complete or not. And if it doesn't complete, then it calls the planner. Um, the planner comes up with a plan. I don't know what the logic is here, but using the LLM decompose the task into a set of subtasks P and a Boolean function logic that combines output of the subtasks. Okay. Um, get the outputs for individual subtasks. Yeah, so it kind of goes through each of these in a loop, combine the outputs of the logic, and then this determines if it's completed or not. So I think it's just essentially trying to see if the sequential set of steps for all of the subtasks that were generated made sense in kind of progression, and that determines um, if the entire subtask was completed. So yeah, very basic recursive decomposition, but it's doing this kind of step by step in order to generate the final output. And then, yeah, so this kind of goes more into the details of how these were implemented. For the executor, we use a common React executor for each dataset. To this end, we provide the LLM in the executor with in-context example trajectories for each atomic skill. Atomic skills are inherently task-dependent and thus vary with the underlying environment. Again, yes, this is what I was mentioning. Like, this needs to be defined based off of whatever you're trying to do. So for Alpha World, in which the agent needs to navigate and perform tasks in the household, the atomic skills include taking an object, putting it down at a location, cleaning, heating, etc. On the other hand, the goal in web shop is to buy a product based on user queries. Thus, the atomic skills include searching a specified query, shortlisting products based on the search page, matching if a product satisfies the criteria, and buying the product. Lastly, the atomic skills and test craft. Yeah, so essentially it's just based off of each environment. But I think this is like, it seems simple in these kind of toy environments, but in real world, it's probably much trickier. Because like if you're trying to teach an agent to do like web search and all those types of things, there's a lot of different ways you can decompose these tasks and kind of create these atomic units. So yeah, but anyway, that's how they did it here. Following yeah, at all, we add goal trajectories for 2 tasks, heat and look in the executor prompt for one good goal trajectory for text craft. Yeah, so these are again the atomic skills just kind of listed out here. Again, I think these environments kind of oversimplify it. In the real world, it'll be much trickier. And then the planner, we provide the LLM with a brief description of atomic skills. So again, you have to tell it like what is the lowest level you can go, right? And in context demonstrations of few task decompositions for each data set. Planner includes 6 examples. Find is not an atomic skill for the executor and therefore needs to be handled by the planner. The planner breaks down a given task. Yeah, essentially. Well, what kind of plans they gave it in the in-context examples. And then the controller performs 2 crucial roles in the overall functioning of ADaPT. First, it serves as the communication bridge between planner and executor, propagating salient information across the two depending on the task. Second, since ADaPT is a recursive algorithm, the controller determines the termination criteria using the logical expression from the planner and success heuristic from the executor if a maximum depth Dmax is reached. The controller propagates task salient dependent information. Yeah, so this is essentially just kind of doing this in a little more detail on, and as you can see, they kind of go through this and show that ADaPT is performing better, right? Then Reflection is also a paper that also came out by the authors of SWE-Agent. I'm not entirely sure what this try again with React is, but plan and execute is kind of that overall plan once and then kind of try to see if you can execute that entire plan. And React obviously is kind of the recursive one. So yeah, I think that's the main thing. Oh yeah, this is the other thing I was mentioning about how they handle kind of both the and or. So yeah, show all the examples in figure 1 and 2 show homogeneous logic across subtasks in the plan. Our controller can handle complex logical operations, including both and or operators. Specifically, we provide instructions to the planner to output this logical expressions at the end of the plan with the fixed prefix execution order. We then build a deterministic parser that can parse complex logical expressions that the controller can process. We do so by splitting the logical expression into a series of homogeneous expressions, each passed to ADaPT. Whether the task given to ADaPT comprises of multiple subtasks via connected logical operator, we automatically decompose this task as per the logical expression. Um, so I think that's a fancy way of saying they split on and and or, to be honest. So yeah, so adapted multi-level plans and adapt. It plans put a clean mug on the desk. Um, then it comes up with all of these kind of and related things. Find and take the mug. Um, figures out that like there can be so yeah, kind of I think they just add this in the prompt, but it's kind of doing this reasoning about what things it should decompose sequentially versus it's more like an either or, like it's either here or it's there or it's somewhere else. And those aren't necessarily like a sequence of operations. So based off of that, it it comes up with like a detailed plan, right? So this one is find and take a mug from the countertop, or find and take it from the cabinet, or find and take the mug from the drawer. And then after that, it says clean and put it. So it's kind of composing these ands and ors in a way that makes sense for it to execute. Um, yeah, I think those are the main things that it focuses on. So yeah, I think I mean obviously it's not very hard to implement. Like that's like probably the simplest pseudocode you can find. And then the rest of it is kind of prompting it essentially in order to do these kind of decompositions and iterative reasoning properly. And yeah, you can just kind of see how this works. So yeah, Elf World just kind of it just gives you like this whole scenario where it lays out the environment and tries to get you to do something, and the agent has to try to figure out like, oh, where to move, what to do next, and then recalibrate the environment, pay attention again. So that's kind of how this works, right? Is it's going somewhere, it's planning, executing, planning again, um, and then it's able to get to the end. Um, cool. I think that's it. I mean, we can continue to go through all these examples, but I think the general yeah. Unless you guys have any specific questions, I can dive into those more. I think the most important thing for me is I was just trying to. I think this is a very. I haven't seen like LangChain or Llama Index or anything like implement this type of an agent yet. So I think it makes it kind of appealing, at least to me, to see what's the quickest way to like get this working. I looked through their code base and I don't know. I didn't. I saw mostly information about the environments, but again, I think I don't think the logic here is hard at all. It's mainly just being able to um, being able to properly identify what the different atomic tasks are, and then build that out. Um, cool. Any? Yeah, I think that's it for me. Unless you guys have questions. It's a pretty straightforward paper, but at the same time, I think it's like actually very I don't want to say powerful, but the idea is very useful in the sense that it's definitely issues I've faced a lot when using like React agents, and um, I think it's not that hard to set up this kind of iterative recursive decomposition system.
How do you actually do the models now? Because you are explaining us the way to execute the model. Take a small like feature, use that data set. If it is failing, reiterate. So if that you are not following that, what you are following now?
Sorry, I didn't understand what you said.
So basically, what I learned is like explain that there's a different atomic feature, and if the base atomic feature is failing, go over that.
Yeah, I mean, no, no, it's what it's trying to say. It's like it plans it to take like 5 or 6 different steps. If one of those steps fail, um, it's essentially going recursively in and trying to re-decompose that into multiple steps.
Yes, but
is essentially what's happening. But it also has the it's not like as simple as that, because as we saw, right, there was like the ands and or. So if it's like an or thing, it will first try the few different or suggestions, and if all of those fail, then it tries to like decompose it further. Um,
okay.
yeah, and it kind of combines these plans across the ands and the ors in order to come up with like a stable plan overall.
But if you are not doing this now, this atomic thing, what you are doing now? How you are doing this particular task?
If we weren't, sorry, I still don't think I understood.
I mean, if you are not following this atomic path,
Uh-huh.
like and all, what you are doing now?
I mean, as I said, right, this is building on top of React. So React is just doing what we saw above. It just every step it comes up with something, and then you just do it, and then now it's like, okay, now I'm here. What should I do next? And then it does the next thing, right? So it's like a greedy planning versus plan and act is like the other approach. It just generates one long overall plan and then tries to execute against that. But then the issue there too is like, if you realize you can't achieve something midway, it kind of will fail and like the whole thing goes down, right? So this is the very obvious next step of trying to like create the overall plan. If anything fails, replan, but do that over like a time range, right? So like, don't just do it greedily. Try to expand your quote unquote beam um, from 5 to 10, of number of steps that it'll take to reach your goal.
Okay.
Yeah, yeah, for sure.